Okay, for this first question, you are looking at an aluminum alloy engine block that can be modeled as a solid cylinder, and you're asked to approximate the engine as a short cylinder in order to determine the surface temperature at the center after it has been running for 10 minutes. And then you're asked to calculate the rate of heat transfer due to boiling if all of the coolant hoses break, causing the engine to overheat, and then all of the cooling water is sprayed onto the engine bay. And so these are all of the assumptions, and this is what is given. These are the properties that had to be found. And this is where two-dimensional transient heat transfer in cylindrical coordinates shows up, is in here, where you approximate it as a short cylinder, which is the product of the cylinder and the wall. And so you solve for everything here, noting that the position of the temperature asked for is given using these equations, where our outer is the surface and x equals 0 is the center. And this is what you get. And then to find the boiling convection phase change, you first have to find the excess temperature difference, which is the surface temperature minus the saturation temperature. And this difference is 120 degrees, which is in the film boiling range. And so using the handout, this is the equation for the film flux. And the heat transfer due to film boiling is given by the surface area times the flux, and this is what you get. And for the second question, you're asked to still consider the situation above, but instead we are just looking at the valve cover, which can be modeled as a flat plate with some thickness. And you're asked to derive the energy conduction equation and then solve for it using boundary conditions and determine the temperature at a specific position. And so we have to assume it's steady state, one-dimensional, no reaction, and that temperature and properties are constant. And so you start with the basic in minus out plus generation equals accumulation. And you can break it up into each individual part. And this is what all of the equations are, where there is some heat transfer rate at a position X, and then this is the same thing, but at a position X plus the change in X, and then the generation is that times the volume, and then this is the accumulation. And when you combine it all, you get this long equation, and then you divide by this, take the limit, and also use Fourier's law to get the more general form. And then for this question, we know that thermal conductivity is constant. This is one-dimensional, so it only varies in the x direction. There's no generation, and it's steady state. And so this is the final form of the equation that's useful to us. And you integrate it twice, and this is how you get the temperature at some position. But we don't know the constants, and so we have to use boundary conditions. The first is to specify temperature, which the temperature at position 0 at the bottom of the valve cover was given. And so we can solve for the C2 value, and then at x equals L, this is the top of the valve cover where it's surrounded by the steam from the water boiling. And so we know that conduction equals convection at the surface. And we can get C1, and this is the final form. And then if you want to find the temperature at the position halfway the distance, then this is that. Okay, for the third question, it's looking at the automotive radiator that was attached to those coolant hoses. And you're asked to find the required length of the heat exchanger using the log mean temperature difference method. And so we assume it's steady state and that it's well insulated. We're given the overall heat transfer coefficient and the diameter of the pipe, because we're going to model it as a counterflow double pipe heat exchanger. And then these are the properties for air and water, their heat capacities. And we're assuming that the temperature average for the air is 50 degrees Celsius because we don't know the outlet temperature. And so this is an okay approximation because the heat capacity is about 1007 for a lot of these values in this range, so it probably is not going to change much. And so to find, we first have to find the heat transfer rate, which is this equation, and then using the same equation but for the cold fluid, you can solve for the temperature of the water leaving the heat exchanger, and then you can find the long mean temperature difference, and then using that value you can solve for the length from this equation here. And it's pretty long, so this is not ideal because it requires a large footprint, and so multipass could be added, but ultimately this is probably not the most accurate model for an automotive heat exchanger. It might be some other type than I have shown here. And then for this fourth question, we are going away from automotive stuff, and this is a rubber beach ball that has been blown up by somebody, so it's filled with carbon dioxide, and you're asked to find first the mass diffusion rate, and so steady state mass diffusion can be seen here in this first equation, where all of these values are given, and so you can just plug and chug. And then for part B, this is transient mass diffusion, because you're asked to find the time that half of the initial mass fraction has diffused through the rubber. And so using complementary error functions, you can solve for these values. And once you have eta, you can solve for t. And this is the value that you get. For part C, this is where radiation heat transfer shows up, because you have a hot ball being brought into a colder surrounding room, and so some of the heat from the ball is going to radiate into the room, and we can assume that the surroundings are a black body and that the surface is a gray body, and so we can use a simplified radiation equation. And since this is a sphere, so spherical coordinates are also here, we know that the surface area is this, and so we can solve for the total radiative heat transfer rate. And the value is negative because it indicates heat loss from the ball. And then for this last question, we have a membrane separation unit that is used to separate carbon dioxide from a natural gas feed. And you're asked to find the fractional recovery of the carbon dioxide in the permeate stream, as well as determine the required area to achieve this separation. And so this is mass transfer unit operations through a membrane, and the fractional recovery is the partial pressure in the permeate divided by the partial pressure in the feed of carbon dioxide. And you can solve for a lot of these values using a total mass balance as well as a component mass balance for carbon dioxide. And then the permeance is given by the equation of the flux divided by the driving force. But then the area is the molar flow rate divided by the flux. And so combining these two equations, the area can be solved for. And we need the driving force for this separation to occur, which is the log mean pressure difference of the CO2. And so first you have to find of the CO2 coming in and the CO2 leaving. Once this value is given or found, you can plug everything in since everything is known, and this is the required area, which is pretty small. And then as well as this is a low fractional recovery, and so it's not a very good membrane separation unit, especially since 30 mole percent is ending up in the retentate. And so it probably means that less carbon dioxide should be in the feed stream, and some of the pressures should change. And that's all I have for these questions. And thank you very much for listening.